Hello, everyone. Thank you for clicking on my talk. I'm here today to tell you about some of my work as a PhD candidate at Brigham Young University at the Tree Soft Matter Theory Group. This talk is going to be given at the APS March Meeting, and it is about my research on polymer crystal nucleation pathway from free energy analysis. The idea came to us by investigating or becoming interested in the question of how does a polymer crystal nucleate from a melt? In other words, when you lower the temperature of a melted liquid, how does the polymer crystal nucleate? And essentially, this is not a novel question. Many authors have investigated it. For example, here you see in front of you two examples of non-equilibrium molecular dynamics simulations with similar models finding very different results. On the left, Yi et al. Found a cylindrical crystal nucleus, whereas on the right, Hall et al. In a series of papers found that their nucleus was anisotropic. On the left, Yi et al. Found that crystal size is a good order parameter, whereas Hall et al. Found that nematic order is the dominant order parameter. So crystalline order is essentially how molecules fit in crystalline lattices, whereas nematic order is on a larger length scale. It's talking about how polymer chains align in the melt, as you can see from the figure on the right. And essentially, this controversy has led many authors to suggest some new models for the polymer physics. The usual or the traditional way of looking at this is through classical nucleation theory, which suggests a free energy landscape or a free energy path along crystalline order. Essentially, when you lower the temperature below the melting point, a melt that you see here on the left becomes metastable. What that means when it comes to a free energy surface is that it has a higher free energy, meaning it's less stable, than the true stable state, which is the crystal. And it happens that this process, according to CNTP, is activated, meaning there needs to be significant free thermal fluctuation for the melt to form a small crystal nucleus with enough free energy to overcome the barrier. Now, the opposite, or perhaps more modern way of looking at this, is through the SOMM hypothesis that says that it's not crystalline order that's important, rather it is nematic order, again, which means how polymer chains align, and it is what forms the transition state. So we believe that we can study this. You see, non-equilibrium MD experiments are problematic because they're not at equilibrium, whereas all of these models suggest a certain shape of the free energy landscape at equilibrium or near equilibrium. So how can we investigate this? And again, the benefit of this is, of course, we can know what's on this x-axis. We can know the relevant importance of the order parameter, what is the transition state, etc., etc. And we believe we can do this with equilibrium Monte Carlo simulations, with advanced sampling methods. We have built phase diagrams using Wang-Landau Monte Carlo, and we plan to analyze free energy landscapes with an expanded ensemble density of states method. I only have time to talk to you about the second arc. Here goes. Okay, before I show you the cool results we have, we got to go through some boilerplate stuff. The most important boilerplate stuff is talking about the potential model we used, i.e. what kind of polymers are we simulating. First of all, we have hard spheres. That means that the beads cannot overlap. We also have constant bond lengths because we don't not believe that that length scale is important to the process of crystallization. And finally, and most importantly, we incorporated a stepwise bending stiffness through penalizing flexible angles, i.e. we are incentivizing the polymer chain to be aligned and parallel so we can see nematic order come about. And we put these polymers in a big box and we move them while respecting their thermodynamics, and we expect the phase behavior to depend on density and temperature. So one more slide of boilerplate. We are using this excellent method called expanded ensemble density of states to build the free energy landscape. Not only is its output the free energy, but also its input is the free energy. And here's how it does it. Initially, you initialize your simulation by setting all of your free energy across your order parameter to being equivalent, i.e. every value of the order parameter and therefore state defined by that order parameter is equally likely. And through the simulation, through an iterative code, you approach the real free energy. And we are utilizing this code to build a two-dimensional free energy landscape with respect to changes in crystal order and nematic order, so we can better differentiate their effect on this free energy landscape. And we will use Q6, the Steinhard bond order parameter, to calculate or quantify crystal order, and P2, the second order Legendre polynomial, which shows you how parallel and aligned your system is. Okay, well, finally we get to talk about some results. So what you see in front of you here, my friends, is the free energy landscape. You have on the y-axis P2 or nematic order. You have crystal order or Q6 on the x-axis. And since this is a two-dimensional free energy landscape, put on a 2D diagram, we have chosen to represent free energy values with color. So for example, this region here, intermediate nematic order and high crystal order, is highly undesirable because it has a high free energy, as you can see from the color bar. In this region, at low nematic order and intermediate crystalline order is the most likely, since it has the bluest of colors, i.e. it has relatively the lowest free energy of the entire landscape you're looking at. In fact, speaking of lowest free energies, we have two regions of low free energy, and what that means is that this is a temperature of coexistence, or the transition temperature. In fact, it is the TIN, or the isotropic kinematic transition temperature. At low density, we find in the system that there is equilibrium between a melt and a nematic phase, and this melt and nematic phase lack crystalline order, and essentially it's just an isotropic to nematic transition where you have these chains that are amorphous, forming parallel lamella. And the melts right here at low P2, and the nematic phase, as you can see, is at high P2. Now, the cool thing about free energy is we can use some nice math tricks like this, suggested by this awesome paper on the right by Fu et al. Essentially, because systems like to minimize their free energy, the path of least resistance would be the minimum free energy path between those. So essentially what we're looking at is how the system transitions at equilibrium, and what we find is that only changes in P2 matter at low density. Now at high density, again the same system, a higher density, we are looking at a very different free energy landscape. And in this free energy landscape, we have coexistence between a state at low Q6, low P2, and high P2, high Q6. And the state that is at low P2, low Q6, of course, is the melt, as we have already determined. But the state at high P2, high nematic order, and high crystalline order is the crystal state. So therefore, this is T crystallization, and we are looking at T crystallization at high density. Now, we did the same thing. We built the minimum free energy path, which, as you can see, is the path of least resistance. How can we avoid the most red of regions? And essentially, what we find is that the minimum free energy path is along the saddle point. Now, surprisingly, at the transition temperature, i.e. at equilibrium, the minimum free energy path requires cooperative changes in P2 and Q6. So what does that mean? Well, it means that the two free energy diagrams we were looking at before, CNTP and SOMM, are mostly violated. Well, CNTP suggests that crystal order is what we're going to move on. So therefore, it suggests the horizontal path, whereas SOMM suggests something like a vertical path. And we see a very different picture. So to wrap up, these semi-flexible oligomers, they crystallize in a cooperative mechanism. And I think this is a significant result, but even more significant is the utility of these equilibrium free energy landscapes that we will continue to use. What we found is that there's no intermediate between the melt and the crystal, and of course, the cooperative mechanism. And importantly, how general are these conclusions of with the small system? Is molecular weight important? Can we extend this to dynamic simulations that have complex kinetics? And what do more complex intermolecular potentials suggest? Maybe not a hard sphere, and further. I am here to show you some exclusive results. I wish I had more time to tell you about this, but we have tested a more complex system, one with soft beads and a continuous stiffness, unlike our system. And what we found is a very different story. In fact, we found two types of transitions at the same density. Essentially, if you have a melt at a certain density, you quench it to a lower temperature, and at some point you will encounter the TIN, and you will have a transition between your melt and the nematic phase. And then when you further cool at constant density, you will find that that nematic phase at a higher nematic order parameter then transitions and moves in both in Q6 and P2 to the crystalline state. Please note the different orders on the X and Y axis. So essentially, to conclude, I'll tell you what one of the reviewers of our paper said, a delightful reviewer, that this work opens more questions than it answers, and we think, and so did they, that this is a strength of our study. There are a lot of awesome conclusions, and we can't wait to extrapolate them and see how much they apply to polymer theory and to experimental results. Essentially, to summarize, we had one system, the hard sphere rod chains, and we found that neither delta F model was a good fit, whereas the more realistic chains seem to be consistent with the SOMM hypothesis. I'd like to thank the PRF and BYU and the Office of Research Computing for resources, and of course my professor, Dr. Tree, and Dakota, my undergrad. Thank you.